So our next section is section 1.4, and it's titled Continuity and One-Sided Limits. We have talked already a little bit about one-sided limits, so we'll go a little further into that at this point. But let's first encounter the concept of continuity. So continuity at a point. A function is continuous at a point C if the following are true, and they have to all three be true. The function itself has to be defined. So what does that mean? Well, it means that you actually have to be able to plug in a number. So if there's a hole in the graph and there's not another open, a closed-in hole, a closed-in circle somewhere else, then it wouldn't be defined. Okay, so we've had that happen. You saw that happen when we tried to factor things and we reduced them, and then we were able to plug the number in. But if you tried to plug it into the original function, it didn't work. That created a hole in the graph. We talked about that last time. That would be an example of something where part A, or number 1 here, doesn't work. You have to be able to actually substitute the value in at that point. The second thing, number 2, is that the limit, and that's the two-sided limit, right? Limit from both directions has to exist. So in other words, I have to be able to approach the same value. So I can't have a jump in the graph, right? Because that would be approaching different values from the left and the right. So no jumps. And then the last thing is that I can't have the limits being different than the function value. So whatever I'm getting close to has to actually be the function value. So occasionally we've seen something like this graphically. Oops, let me use a pen. Where there's a hole and then it's defined somewhere else. This would actually satisfy conditions 1 and 2, right? There's a function value, that's the closed dot. There's a limit value, it approaches the same thing from both directions. But the limit value, which is the open circle, and the function value, which is the closed circle, they're not the same thing. So this would also be one that falls apart with step number 3 or condition number 3 here. Intuitively, I know you know what continuity means. It means that you can draw and not have to pick up your pencil, right? That's how we think about it. If you can draw the graph without having to pick your pencil up and put it back down at a specific point or around a specific point, then it's continuous. But these are the conditions in sort of a concrete sense of what have to be true. So we've got continuity at a specific point, and it just means nearby the point these have to be true. We also have continuity on an open interval. So for it to be continuous on an open interval, basically we have to have all those same conditions as my previous slide at every point in the interval. So it says a function is continuous on an open interval AB when it's continuous at each point in the interval. And if it's continuous on the entire domain of the function or the entire number line, we call it everywhere continuous. Okay? All right, so we're going to take a look at some function value, or at some limits and some continuity things in our examples. So to start with, we're looking at a few limits. These are one-sided limits. When we did one-sided limits before, we looked at it from a perspective of graphs, and we looked at it from a perspective of a table, right? We're going to look at it here from the perspective of algebra. So what we'd like to be able to do is exactly what we did with the two-sided limits when we used algebra in the previous section. We want to be able to plug the value in, okay? If there's any reducing that needs to happen, we can reduce, and then we try to plug the value in. And the reality is that the plus or the minus after the value doesn't affect it if we can plug the value in. So if we can't, we'll talk about what happens next. But for now, on this one, it works just fine, right? This says 8 from the right. I try to plug in the number 8, and I have no trouble doing so. So this limit is 1/16, and I'm good. On the second one here, if I try to do the same thing, I run into a problem. The problem that I run into is that if I attempt to do this, what will happen? I get 0 on the top and 0 on the bottom, right? And we've talked before about the fact that when that happens, usually means there's a hole in the graph, right? If I've got a 0 on the top and a 0 on the bottom, I've probably got a hole in the graph. So I probably have the ability to actually have a limit. I'm just going to have to do some work to get there. I'm going to have to do some simplification with some algebra. And we encountered one like this last time. Do you remember what we did when we had a radical? We did. We rationalized it. Good job. And this one's a little messier than the one we rationalized last time. Sorry about that. But that's the way it works sometimes, right? Start with easier problems. So the part that's irrational is the part that has the radical, which happens to be the numerator here. So it's the top that I need to rationalize, and that's usually the way it works on these particular problems. Doesn't have to, but it just usually is. So if I'm trying to rationalize this, what would I have to multiply by to get that radical to go away from the numerator? Right, the square root of x plus 3, and I think someone over here said conjugate. Those are both statements that are true. This is the conjugate of the top. And of course, if I do that on top, I have to also multiply by it on bottom. Now, the whole purpose in choosing that is that when I multiply it out on top, this is a difference of squares, which means that the inner terms and the outer terms are exactly the same, but opposite signs. So they cancel each other out. They add to 0. And so what ends up happening is that I only have to worry about multiplying, the first terms together and the last terms together. So on the first terms, the square root of x times the square root of x would be x. And then negative 3 times positive 3 would be negative 9. I mentioned last time that it's really not helpful to distribute the denominator here, okay? And it isn't. And of course you can see hopefully pretty quickly why it isn't helpful. Why would it be unhelpful on this one to distribute the denominator? Yeah, it'd be much harder to see the cancellation that you're able to do, wouldn't it? But if I leave it in factored form, I can see the cancellation pretty quickly. So I do in fact get to cancel out the x minus 9 because they're both factors of the numerator and factors of the denominator. I'll mention this again. Do you see how I'm writing limit every single time? You should be too. The limit's still there. Each of these steps is equal to the step before, as long as I don't lose that piece until I plug the value 9 in. So on the top right now I have 1. Remember, we're dividing here. Yes, Emma?
Would you allow us to, like, if we had like a whole line on a notebook paper, just put equal, would you?
Yes, you can do that. So you're asking whether or not you can sort of draw it sort of horizontally instead of vertically. Absolutely. I have no problem with that as long as, again, you still remember the limit part. Yeah, but that's totally fine. Yeah, so it could look like this, and then this piece would be here.
Okay.
Yeah,
So
that would be
The
fine.
piece there still has to have a limit.
Yep, but the limit still has to be there. It still has to say limit. Absolutely. Okay, is that all right? Yeah, I know for me it's a lot easier to think vertically, but I know for some of you it's a lot easier to think horizontally, and that's fine. They're the same thing as long as we keep the limit, okay? In the denominator on this one now, I have square root of x plus 3. And can I now plug in my 9? Yeah, it can. So now I have 1 over the square root of 9 plus 3. And the square root of 9 is 3. So this is 1 over 6. So I do, in fact, have a limit. And again, it really didn't matter on this one that I'm coming from the left or from the right, because I am able to plug it in at the end. It's when I can't plug it in at the end that I have to do something different. So let's take a look. The next one actually matters whether you're coming from the left or the right. And the reason it does is because what do you see happening on this one that we haven't had so far? Absolute values. And absolute values are a little tricky. I don't know if you remember what an absolute value graph looks like, but an absolute value graph looks like a V. What happens is that every x value that's positive will have the same y value that's positive, yeah? But if the x value is negative, we also have the y value that's positive. So that's why it creates that V shape. So here's the catch. When you define an absolute value, it's defined like this. And I'm sure you've seen it before. Every time I show it to my elementary ed majors, everybody gets a little nervous, and maybe even some of you are nervous you're seeing a negative. Remember, negative just means the opposite of. So all that second line is saying is that if I have negative values, then the y value is the opposite of that. And the opposite of a negative is a positive. So we need to know on this one, am I coming from the left or the right? Because I need to know whether or not that absolute value of x on the top is actually representing x, the same value it already was, or the opposite of x because it happened to be negative. And this says that I'm coming from the negative side of the graph, correct? So I'm on the second line of this piecewise definition. It's the opposite of, because these are negative values. If I were trying to evaluate this and plug numbers in, I'd be putting negatives into this. And if I put negative into the numerator will change to positive while the denominator will stay negative, right? So this numerator, because I'm coming from the left, is actually equal to negative x. It's the opposite. Because I keep plugging in, I'm going to be plugging in negative values. If we did it from a table, we'd be plugging in like negative 0.1, negative 0.01, like you did on your quiz. So how will negative x over x reduce? Don't overthink it. It's negative 1, absolutely. And when there's no numbers present, then that simply is a constant, and that's my limit value. Make sense? So this right here would have a limit value of negative 1. If we were coming from the right-hand side, what would change? The numerator would be different. What would the numerator be? It would be positive x. And if I had positive x over x, I'd end up with the value of 1. So this one's actually going to be discontinuous. From the left-hand side, it's at negative 1. And from the right-hand side, it would be at positive 1. And I would have a jump in the graph. That's what would happen on this particular function. Okay? So let's talk a little bit more about discontinuities, because I just mentioned one. There's actually two types of discontinuities, and we've seen both of them happen. One of them is called removable. Removable discontinuities, they're really just holes in the graph, where if I could just fill in the hole, I'd be good to go. Okay? So this occurs when f can be made continuous by appropriately defining or redefining f of c. Redefining means like if you could fill in the hole. If you could rewrite the function in a simplified way that allowed you to plug the value in, which we did last time in class, it's a removable discontinuity. It's a hole in the graph. The last example we just did is an example of a non-removable discontinuity. It's a jump. This occurs when f cannot be made continuous by defining or redefining the function value. I can't simply fill in a hole and remove the jump, right? It's not possible. And I can't connect the two because then it wouldn't be a function, right? Can't just connect the dots. So removable continuities translate to holes, and non-removable continuities translate to jumps. So we're going to do a couple of examples where we're trying to decide which kind of discontinuity we have. So it says, find all the x values at which the function is not continuous. Which type of discontinuity do we have? So which of the discontinuities are removable, basically, is what it's asking. So what is the value where this is not continuous? 0. Can't plug 0 in, right? So the issue is that x equals to 0. I hope you remember what this function looks like. If you don't, you have a grapher and you could look. But do you remember, by any chance, what happens at 0 on this graph? What is it? It does. Do you remember what we call what's happening at 0? It's an asymptote. Good job, Jackson. I have an asymptote there. So this is actually an asymptote, just sort of as a reference point for us when you're looking back later. Is an asymptote a removable discontinuity or a non-removable discontinuity? It's non-removable. It's a jump. It's an example of a type of jump. Right. So this is non-removable. And there's lots of reasons for the why. Like if you wanted to say it, you could say because it's an asymptote. Or you could say, let me say it better. There is an asymptote. You could say at the y-axis, or you could say at the line x equals 0. You could say, because I can't cancel out the 0 in the denominator. There's no way to simplify this function. That'd be another reason why you could justify it. I can't remove the 0 in the denominator. If I can't remove it, it's non-removable, right? That's another thing you could say. Yeah, those are the two that I have written down. Okay, let's take a look at the next one. A little more going on in this particular function. So how am I going to find the places where this is not continuous? Got it. Factor the denominator. So this denominator, I'll leave my numerator the same. Factors how? Good job. Cooper, right? Connor, oh man, I was close. It's only one letter off. Yeah. All right, x plus 2 and x minus 5. Okay, so if we were working with this problem, what would we do next? We would cancel the x plus 2's, right? And we'd be left with 1 over x minus 5. Now, there's two questions. The first question is, where is it not continuous? Is that the only place? Yeah, it's not continuous at 5 and at -2. Okay, still not continuous at -2. But different things are happening because one of those reduced, it was removed, and the other one was not. So, what happens at the 2, the -2? There's a hole. So there's a removable discontinuity. And like you said, it's a hole there. Again, if you want to justify why, it's because it was actually able to reduce. Right? I was able to eliminate it, to remove it by canceling it out with the numerator. So then what happens at x equals 5? Removable or non-removable? It's a vertical asymptote, so it's a non-removable. And again, because there's an asymptote there, because I cannot cancel it with anything in the numerator, I can't eliminate or remove the factor.
So I have a question.
Yeah.
On the, how did we get the x equals -2? Because it was, is that?
You set it equal to 0.
Got it.
Yeah, so you get the discontinuities. In fact, it was really not from the numerator, technically, it's from the denominator. But you set each of the factors in the denominator equal to 0.
Okay, it's another
Uh-huh.
verse. Okay, so
Right.
Thank you.
Yes. Okay, so the discontinuities are happening when the denominator is 0. That's where they're catching up
So
with
you
us.
need to do it with both.
Yes, exactly. All right, so let's take a look a little bit more about these limits. When does a limit exist? So let f be a function, c and l real numbers, and we'll say that the limit of f of x as x approaches c is the value L, and it happens if and only if the two one-sided limits are also L. So this is just another way of writing the same thing that we've had before. 1 or 2 lessons ago, I can't remember. But in a compact way. Before we talked about this side limit has to exist, this side limit has to exist, and then both of them have to equal each other, right? This just pushes it all together into one definition. Now, when we're dealing with a function that is described in one compact way, right, it's just got one single equation, looking for holes in the graph, like denominators equaling 0 or asymptotes, is kind of the only issues that we have. But we also have functions that are defined piecewise. I showed you one of them, although it was compact over here before. This one's actually a fairly piecewise function because it matters whether you're on the left or the right, correct? The negative side or the positive side of the graph. But some functions that are piecewise are actually defined in pieces too. So this would be an example of a piecewise function. So the directions on this one are that we want to figure out what this generic a value, this random a that's thrown in here, would have to be to make the function continuous. Now, we've talked about the fact that when we have a polynomial, it's automatically continuous, right? Think about the graph of a parabola. There's no holes, there's no problem spots. This one is an example of a line, right? Like y equal mx plus b. Lines are continuous. So if there's any problem, the problem is going to be that part of this graph is a parabola, right? Like this, and part of this graph is a line, and we got to make sure that the line and the parabola meet so that there isn't a jump or a hole. Does that make sense? We have to make sure that happens. And the reality is that this slope value is what we're trying to find. So in some sense, we can shift things around to make what we want to have happen. It wasn't quite like what I made it look like, but it'll be more like this. I have this curve, and I know that it crosses here, and I have to make sure that I've got the right steepness to make it work, because I'm looking for a slope value. Okay? So how do we make that happen? Well, we actually make that happen by looking at the one-sided limits. So let's take a look. We're disconnected potentially at this particular x value, x equal 1. Right? So one of the graphs starts at 1 and goes to the right. That's our parabola. The other graph is the left-hand side before the value of 1. So when I'm looking at these limits, I'm going to have a limit as x goes to 1 from the left and a limit as x goes to 1 from the right. And it will fall on different pieces of this graph. So if I'm on the left-hand side, which piece of this graph am I on? The 3x squared or the ax minus 4? The ax minus 4. Emma, how do you know?
Because it's x is less than, or less than 1, so it's like approaching 1 from the left side.
Exactly. Very good. So the pieces at the end describe for us which piece to be on. You just have to pay attention and be careful that you're looking at them correctly. This second equation is for the left-hand side of my graph. And I can plug in the value 1, right? That's what we were just doing on the previous problems, is that it doesn't matter that there's a negative or a positive. I can evaluate this function. It's the value for x. So this is actually a times 1 minus 4. So it's a minus 4. The second one from the right, then must be the 3x squared part of my piecewise function, right? Yeah. So there's no a in this one. That's very friendly. So I can plug the number 1 in very easily. 1 squared's 1 times 3 would be 3. And what I want in order for this to be continuous, right, what this says over here is that the function is continuous. The limit exists if it's the same from both directions. So I want these two one-sided limits to be equal. What does a have to be to make that happen? 7. And if it were more complicated, you could actually set up the equation to solve it. But yeah, adding my 4, a7. And that's exactly what it asked me to find. What a value would make it work? You could graph this, right? You could graph each of these individually. There are ways to graph them piecewise. I don't really want to get into that too much because we're just not going to see it happen enough to make it worth my time today to show you. But if you want to see it in my office, come check it out with me. I can show you how to put that in. However, at the very least, what you could do is you could graph the 3x squared, and you could graph the line that would be 7x minus 4, because that's what we just found, right? And you could see that when it's 7x minus 4, that at this particular point right here, is x equal 1, that they meet. And you could see that on a graph, if you want to look at it from a graphical standpoint. All right. We talked about continuity on an open interval, so we're going to talk about continuity on a closed interval next. A function is continuous on a closed interval AB when f is continuous on the open interval AB, and the one-sided limits as you approach a from the right and b from the left are actually the function values. A function is continuous from the right at a, from the left at b. So visually speaking, I'll just use a parabola as an example. As long as I actually have closed-in circles at the end, right? I don't have something like an open circle here with another closed-in circle up here. Can't do that. That's not appropriate. So that as if I approach this as A from the left, or from the right, or B from the left, I end up at closed circles. They actually have closed-end points. There are ways to combine functions that preserve continuity. So some properties of continuity. If b is a real number, f and g are continuous at x equals c, then the functions listed below are also continuous. You could multiply a function and it wouldn't change continuity. That's number one. You could add or subtract two functions and it's not going to change continuity. You could multiply functions and it won't change continuity. And you can divide functions as long as the denominator is not 0 and it won't change continuity. And none of these things should be very surprising because continuity is a direct result of limits. And we had all these things for limits already. Okay, the one last thing in this section is actually where your written homework is going to come from. The last piece of information in this section is called the Intermediate Value Theorem. And it's a very intuitive idea. I'll draw you a picture, but let me show you the actual theorem first. If f is continuous on the closed interval AB, and the two endpoints are not equal, f of a does not equal f of b. K is a number in between f of a and f of b. Then there's at least one number c in the interval AB such that f of c equals k. So that was a lot of symbols to show you something that you would go, oh yeah, well of course. Okay, so here's an A and here's B. And they're saying that the y values for f of a and f of b are not the same. So this is f of a, and this is f of b. So far, so good. Because it's continuous, I have to be able to connect those two dots. Maybe it goes straight there like a line. Maybe it dips down. Maybe it does all sorts of weird stuff. That was not okay because that wasn't a function. Okay, but somehow they're connected. Sort of the worst case scenario for this description is that there's a single, like, connect the dot line maybe between them. What it's saying next is that for every value between f of A and f of B called K, there has to be a corresponding C value between A and B. It's basically saying there can't be a hole. But you know there can't be a hole because it's continuous. You had to pass through every value to get there, maybe more than once. If your graph did something like I drew a little bit earlier, right, the K value would be over here, right, the C value would be over here. But you might actually cross it several times, right? It might have 2 locations. That'd be okay. But you've got at least one location where it will work. So I'm going to show you how we actually go about using the intermediate value theorem because this is what your written work would be for, okay? Can't really do web assigned problems on this type of a problem. We're going to verify something. It's kind of like when you do trig. Those of you who had trig here last semester, when you do verifying identities, it's really difficult to do that on my math lab. Partly because there's so many different options and ways you could do it, but also because if I just give you the multiple choice answer, well, I know the answer. I know where I have to end up, right? I need to see the work to get there. That's the whole point of the problem. Same thing here. Verify the intermediate value theorem applies and use it to find the value of C guaranteed by the theorem. So what does it mean to verify that it applies? Well, it means to verify that f of A does not equal f of B. That's the first thing we're going to verify. Well, it doesn't matter if it's first or second, but that's one of the things we have to verify. And the second thing that we have to verify is that f is continuous. And the reason that I can say those two things is because that's what the definition says. It says it's continuous and that the endpoints don't match. And as long as those two things happen, then the intermediate value theorem will apply. So continuity is usually pretty easy and often forgotten because we just sort of assume it. I'll start with that one, part B, if you will, or number 2, the way I've written it down here. Why is this function continuous? Because it's a parabola. We had a whole list in a previous section, I can't remember if it was 1.3 or 1.2, of things that were continuous simply because they are certain types of functions. Parabolas is polynomial. Linear is a polynomial. That was one of them. All right, the second one, f of B and f of C, or f of A and f of B. That's these endpoints here. I need to make sure that f of 2 and f of 3 are not equal. That's what I have to show. I can't just say it either. I wrote it down right now, but I need to show it. So if I'm doing that, I need to figure out what is f of 2. Well, it should be 2 squared minus 7. What is that? It's negative 3. Good. And I have to do f of 3. So that's 3 squared minus 7. Yep, and that's 2. And these are, in fact, not equal. Okay? So those two pieces tell me that the intermediate value theorem applies. The next thing then it says is to show that we actually can find this C value. So we're actually going to take our f of x function, which is x squared minus 7, and we're supposed to be able to get that to equal 1. So we set it equal to 1. And I need to solve x squared minus 7 equals 1. So what could I do for that? There's more than one way to do the problem, but what would you try to do next? I'd move the 7 as well. So I have x squared equals 8. Then what? Yep, square root. So this actually gives me 2 values. Why? Yeah, square roots give me plus and minus, right? I get positives and negatives. So I actually get two values from solving this. And how can I simplify square root of 8?
2 square roots of 2.
Good, 2 square roots of 2. Now, I need to be careful because according to the Intermediate Value Theorem, my C value that I'm looking for has to be between A and B. And both of these values are not between A and B. They could be, like I could get 2 answers here. That's a legit possibility. But these simply aren't. They're not both between A and B. Which one is? Yeah, the positive one. So C is 2 square roots of 2. And you may or may not just know that off the top of your head, that 2 square root of 2 is really between 2 and 3. How could you double check just to make sure you didn't make a mistake there? Yeah, plug in the calculator and get a decimal approximation, right? So what is approximately 2 square roots of 2? Somebody tell me. 2.83. Thank you, Emma. So 2.83, is that between 2 and 3? Yeah, it is. So 2 is in fact less than 2 square roots of 2. It is less than 3. So we found the fact that we needed. I'll actually write that here. It's approximately 2.82. Okay, so you have a web assigned to do for this. It's going to be about the earlier stuff we did. You have just 2 problems for written work that I will collect next time, and that will be over intermediate value theorem problems, okay?